Okay, today we're going to start section 4.1 on vector spaces. So we'll start with the definition of a vector space. You'll probably want to have your book out with you because we're going to refer back to this definition quite a bit. So in your textbook, it's on page 217. There's a lot to this definition, so we'll spend a little time just talking about it before we move on from there. A vector space is said to be a non-empty set V of objects called vectors. Okay, now let's stop there because that's a little bit odd. It's a set of objects called vectors. I want to make the point here that when the author uses the term vector in this context, he's not necessarily talking about a vector of the type we're familiar with, like in R2 or R3 or so forth. Yeah, he's using it in a more generic sense, and I actually like to use the term object just to keep from confusing you between exactly what he's referring to by using the word vector. And as we go along today, you'll kind of see what I'm talking about here. Okay, so starting over, a vector space is a non-empty set V of objects on which are defined two operations called addition and multiplication by scalars, which are real numbers. Now again, this seems sort of odd, I would think, to you, because he's saying there's two operations, and instead of saying two operations, addition and multiplication by scalars, he's saying there's two operations called addition and multiplication by scalars, which is kind of an odd way to phrase it. And the reason why he says it like that is because since these objects are not necessarily vectors in the traditional sense that we're used to, then addition and multiplication by scalars are not necessarily defined as we're accustomed to. Okay, they can in fact be defined in any way that you would like, as long as these properties here are satisfied. So we're in an abstract sense here. Okay, we're talking about objects and operations, so don't assume that we're talking about vectors in the traditional sense, nor addition and scalar multiplication in the traditional sense. Okay, so we have this collection of objects and these two operations, and they are subject to the 10 axioms given here. And these axioms must hold for all vectors u, v, and w in the set V, and for all scalars C and D. Okay, so I've kind of highlighted some because some are a little bit more interesting than others. Number 1 says the sum of u and v, denoted by u plus v, is in the set V. Okay, so it just says if you take any two vectors from the set and you add them together, then you get another vector that is still in the set. As we'll see in a minute, this property is called closure, or we say that the set is closed under addition if this property holds. Okay, 2 and 3 are some standard properties. Number 2, we have the commutative property, 3, associative. The number 4 says that in the set V there is a zero vector, such that when you add it to any vector in the set, you just get that vector back. Okay, so u plus 0 is equal to u. Okay, so notice number 1 is referring to an element that has to be in the set. Okay, if u and v are in the set, their sum has to be in the set. Number 4, also saying that there has to be this zero vector in the set. Okay, so, and we'll see that number 6 kind of follows along with that too. Number 5, for the first, says for each vector in the set, you have another vector such that when you add it to the first, you end up with a zero vector. So it's essentially saying that every element has an additive inverse in the set. Then number 6 says the scalar multiple of any vector by a constant c is denoted by c times u, and that is in the set. Okay, so this says that when you take the scalar multiple of any vector in the set or any object in the set, the result is also in the set. So you can see that number 1, number 4, number 6 all are specifically referring to whether or not particular elements are in the set. And that will be important as we go along. Numbers 7 through 10 are again standard sorts of properties. We have distributive properties, and number 10 we have a multiplicative inverse property. 1 times any element in the set is equal to that element. And you might be looking especially at number 10 and going, well, when would that ever not be the case? And the answer is going back to what I'd said originally, is that the set V can contain items other than just vectors like from R2 or R3. And these operations, addition and scalar multiplication, can be defined in non-standard ways. And so based on that, then sometimes it could be the case that number 10 would not be true. Okay, so let's start with R2. That's a simple set to think about. And let's talk about whether R2 is a vector space. The answer is yes, because all the properties except 1 and 6 were in fact explicitly given in section 1.3. So if you want to go back to page 32 and check that out, all the properties except 1 and 6 are explicitly listed there. So let's think about 1 and 6. Number 1, we want to know if you take 2 vectors from R2 and add them together, do you get another vector in R2? Well, here's 2 vectors in R2, A, B, and C, D. When we add them together, we get A plus C, B plus D. That's another vector in R2. So the answer is yes there. Number 6, if you multiply a vector in R2 by a scalar, do you get another vector in R2? Okay, is it closed under scalar multiplication? And here we see multiply a vector times a scalar, we get another vector in R2, both of whose components are real numbers, and therefore R2 is a vector space. And in fact, the set of real numbers, set of all vectors with 2 components, which is R2, R3, and Rn in general are all vector spaces. Going back to these property 1 and property 6, just to take a second look at those. Property 1 said that if you take any 2 vectors from the set and compute their sum, then it is also in the set. Okay, and if that is true, we say that the set is closed under addition. Property 6 says if you take a scalar multiple of a vector in the set, then the result is also in the set. Then if this is true, we say that the set is closed under scalar multiplication. Okay, so keep those terms in mind. Let's move on and consider another set. Here's another set. This is a subset of R2. So I'm saying we have a set S here, which consists of vectors of the form x0, where x is a real number. Okay, so basically everything in R2 where the second component is 0. If you think about this graphically, it's just saying that the y component is 0. So therefore, graphically speaking, S would just be the x-axis. So I want to know, is S with the operations of addition and scalar multiplication as traditionally defined, okay, what you're used to, is S a vector space? Well, again, axioms 2 and 3 and 7 through 10 follow automatically. since S is a subset of R2, because 2, 3, and 7 through 10 are true of everything in R2. And I'm assuming here that you got your book open so you know which of these I'm referring to. The other axioms depend on certain elements being in the set, so we have to look at this closer. So number 1, is S closed under addition? I.e., if you take 2 elements in the set, do you get another element in the set? You take 2 elements in the set and add them together, do you get another element in the set? Well, here I've taken a couple of generic elements from the set, U and V, and if we add them together, as I've done here, notice that you get this vector of this form, U1 plus V1 in the first component, 0 in the second component, and this vector is in, it should be a S there. This vector is in S instead of V. Since U1 plus V1 is a real number, let's pause here. Why do we know that U1 plus V1 is a real number? The reason we know that is because U and V are both in S, and therefore U1 has to be a real number, V1 has to be a real number, so we add 2 real numbers together, we get another real number. Okay, so we know the first component's a real number, second component is 0, and that's what it takes to be in the set S. So S is closed under addition. About number 4, does S contain a 0 element? Does S contain a vector 0 such that when you add 0 to any vector in the set, you just get that vector back? Well, the obvious choice would be 0, 0. So the question is that vector in S? And the answer is yes, because remember, to be in S, the first component has to be a real number, which 0 is, and the second component has to be 0, which we have here in the 0 vector. Okay, number 5, does each element have an additive inverse? Well, if we start off with a generic element of the set, say U equals U1, 0, we can add to that this vector negative U1, 0, and it is in the set. How do we know that? Well, if U1 is a real number, then negative U1 has to be a real number, and we have the second component 0. When we add those together, we get the 0 vector. Is S closed under scalar multiplication? So if we take a generic element from the set, multiply it by a scalar, do we get another element in the set? Well, here's a generic element of the set, U equals U1, 0. C is a scalar, that just means it's just any real number. And if we multiply C times U, we end up with CU1 in the first component. Now that has to be a real number, which it is, because C is real, U1 is real. Got the product of 2 real numbers, and that's another real number. And the second component is 0. That's what it takes again to be in S. So S is indeed closed under scalar multiplication. And at this point we've established that all 10 of the axioms are satisfied. So S, our set S, is a vector space. Okay, now it turns out that when you're dealing with subsets of known vector spaces, just like we were here, S was a subset of R2, then we really need to only examine 3 of these properties to see if the set's a vector space. And actually, we typically call it a subspace of the larger vector space, even though it is actually in itself a vector space. Okay, so there's the 3 properties are given here. We say a subspace of a vector space V is a subset H of V that has 3 properties. The 0 vector of V is in H. H is closed under vector addition, and H is closed under scalar multiplication. Okay, so if we want to check to see if a set is a subspace of a vector space, We need only check these three properties. Alright, so let's do that here. Here's another set, T. And T is a subset of R2, and it consists of all vectors where the first entry is any real number and the second entry is a 2. So I want to know is T a subspace of R2? So looking at the first one, does T contain the 0 vector of R2? Right, that was the first requirement to be a subspace. So I'm asking, is 0, 0, is the vector 0, 0 in T? And if you look up here at T, remember, what does it take to be in T? First component's any real number, second component's 2. So we look at 0, 0, does that fit that bill? No, it doesn't. Why not? Because the second component here is 0. To be in T, the second component has to be a 2. Okay, so 0, 0 is not in T. And at this point, we could stop and say, nope, T is not a subspace of R2 because it doesn't contain the 0 vector of R2. But for practice, let's just keep going and consider the other two conditions. So here's T again. Is it closed under addition? So if I take two elements of T and add them together, do I get another element of T? Well, here's a couple of generic elements of T. If I add them together, what happens? Oops, look at that second element here. Second element in the sum of these two is a 4. So this is not in T, right? Because to be in T, your second component has to be a 2. Here it's a 4. Okay, so T is not closed under addition. How about scalar multiplication? Is it closed under scalar multiplication? Well, let's take a generic element of T. Here's one. Got a real number on top, 2 in the second component. We multiply by scalar, and what do we get? We get this vector. Actually, we shouldn't get that vector. That V1 should not be there. I apologize for that. It should be just CU1 in the top, 2C down in the bottom. Make a note of that. So again, this plus V1 shouldn't be here. But let's look. What's important really is the second component, the 2C here, because what we want to know is that 0? And the answer is, well, it's 0 only if C is 0, and C is not restricted to be 0, and therefore we can easily come up with a counterexample to show that we can take a scalar multiple of an element of T and end up with something outside of T. So T is not closed under scalar multiplication. Alright, we'll make one more note. Alright. So in this case, this set T failed all three of the subspace tests. Again, if you were simply trying to determine if T is a vector or a subspace of R2, you only need to find one that it fails, and then you could stop there. I just showed you all three just for practice. Okay, so as I said before, these vector spaces such as R2 and R3 and Rn, those we are familiar with, but there's a lot of other ones in which the elements don't look like traditional vectors. So let's kind of examine that a little bit. Consider this set I'm calling M sub 2 by 2, which is the set of all 2 by 2 matrices, okay, where all the components are real numbers. Turns out that M sub 2 by 2 is also a vector space, even though its elements are matrices instead of vectors in the traditional sense. So let's go back through those properties with M sub 2 by 2 in mind. Okay, so let's start off and suppose that A, B, and C are 2 by 2 matrices, and that P and Q are scalars. So property number 1, if we add A and B together, do we get another 2 by 2 matrix? Right? This is saying, is M sub 2 by 2 closed under addition? And clearly it is. If you add two 2 by 2 matrices together, you get another 2 by 2 matrix. All right, here are the second and third properties. Those fall straight out from properties of matrices. Number 4, is there a zero matrix? All right, is there some 2 by 2 matrix such that you can add to any other 2 by 2 matrix and get that same matrix back? Well, clearly there is. It's a matrix with zeros in all the positions. And number 5, if you add negative A to A, you get the zero matrix. Number 6 is M sub 2 by 2 closed under scalar multiplication. So if you take any 2 by 2 matrix and multiply it by a scalar, do you get another 2 by 2 matrix? And of course you do. So it's closed under scalar multiplication. And then these final 4 properties fall straight out from what we know about matrices. So M sub 2 by 2 is indeed a vector space. Another one about polynomials. Polynomials are some standard examples of vector spaces. Let's first start with P sub 2. P sub 2 is the set of all polynomials of degree 2 or less. Okay, so we wanted to write it in formal terms. It would look like this: A naught, set of all A naught plus A1 times T plus A2 times T squared, where A naught, A1, A2 are real numbers. So here's some sample elements of P sub 2. 3 plus 2T. Okay, here 3 is A sub 0 is 3, A1 is 2, A2 in this case would be 0. 4t squared, that's in there. 8t squared minus 13t plus 45, that's in there. Okay, any polynomial of degree 2 or less. Okay, and P sub 2 is indeed a vector space. Let's look at these properties in terms of P sub 2. So if we add 2 polynomials of degree 2 together, do you get another polynomial of degree 2? Okay, well, yes you do. Here's how that works. If you've got 2, let's call it P of T, which looks like this, Q of T, which looks like this, and if we add them together, then we get this polynomial here, which is again of degree 2 or less. Okay, they satisfy the properties 2 and 3. I can let you explore that some more. Number 4, do you have a zero element? Is there a zero polynomial? Well, yes there is. It's just 0. If we add 0 to any polynomial, we get that same polynomial back. If we negate all the coefficients in a polynomial and add it to the original one, we get the zero polynomial. Number 6, is this set of polynomials closed under scalar multiplication? So if you multiply any polynomial of degree 2 or less by a scalar, do you get another polynomial of degree 2 or less? And the answer is yes. Okay, here, multiply by a scalar, and we get another polynomial of degree 2 or less. And again, 7 through 10 kind of fall out pretty straightforwardly. Here's another set. This is a subset. Q sub 2 here is a subset of P sub 2. Here I've got all polynomials not of degree 2 or less, but all polynomials of degree exactly 2. So the way I've defined it is in this form, looks like P sub 2 with this addition. A sub 2 has to be non-zero. Okay, so that makes it where you're going to have a second degree polynomial. All right, you're going to have a sub 2 not equal 0, so you're going to have the t squared term showing up. So I want to know, is Q sub 2 a subspace of P sub 2? So to show that it's a subspace, we need to show that it satisfies those 3 properties. Right, includes the zero element, closed under addition, closed under scalar multiplication. So is that the case? Well, let's start with number 1. Does Q sub 2 contain the zero element of P sub 2? Well, the zero element of p sub 2 is the zero polynomial, right? Just 0. So is that in q sub 2? And the answer is no, because, go back up and look at the definition of q sub 2, a sub 2 can't be 0, right? But down here, in the zero polynomial, a sub 2 is 0. So q sub 2 does not contain the zero element of p sub 2. So we could stop right here and say, nope, q sub 2 is not a subspace of p sub 2. But again, just for more experience, we're going to go on and look at the other two. So the second one is q sub 2 closed under addition? So if we add any two elements of q sub 2 together, do we get another element of q sub 2? Or if you add any two polynomials of degree exactly 2 or less, not or less, a degree exactly 2, do you get another polynomial of degree exactly 2? There it is there. So here's an example. Let p of t be 6t squared minus 3t. That is in q sub 2 because we've got a 6. Okay, the a sub 2 term is not equal to 0. And here's q of t, where the coefficient of t squared is not 0. So we've got two polynomials here of degree exactly 2. When we add them together, what happens? The t squared terms go away. We're left with negative 3t plus 5, and that is not of degree exactly 2. So q sub 2 is not closed under addition. About scalar multiplication. If we multiply a polynomial of degree exactly 2 by a scalar, do we always get another polynomial of degree exactly 2? So think about that. Is there anything so you start off with any sort of polynomial that's degree exactly 2, and you multiply it by any scalar, do you always get another polynomial of degree exactly 2? And if you don't think about that very long, you might say, well, yeah, you multiply it by anything and you're going to get another polynomial of degree exactly 2. And that's almost always true. But there's one coefficient, one scalar you can use. If you multiply by 0, then you get the 0 polynomial, and it is not of degree exactly 2. So this means that q2 is not closed under scalar multiplication. So q sub 2 here failed all three of the requirements to be a subspace of p sub 2. Yeah, it only has to fail one and to not be a subspace, but this one, in fact, failed all three properties. Okay, let's look at one more. Let's look at z, set of all integers. Okay, and I want to know, is z a subset of the real numbers? A subspace of the real numbers, excuse me. Clearly it's a subset of the real numbers. Alright, so we want to know, number one, does z contain the 0 element of the real numbers? Well, the 0 element of the real numbers is just 0, and 0 is an integer, so the answer here is yes. Is z closed under addition? Okay. If you take two integers and add them together, do you get another integer? And the answer is yes, because the sum of any two integers is always an integer. So we passed number 1, we passed number 2. How about number 3? Is it closed under scalar multiplication? So if we multiply an integer by a scalar, do we always get another integer? Let's think about that. Trick here is that the scalar could be a real number. You don't have to multiply it by an integer, right? Scalar just means a real number. That real number might not be an integer. So if we multiply our integer by a non-integer, then we open up the chance that we could end up with a non-integer. So the answer is no, it's not closed under scalar multiplication. And here's an example. If I multiply 0.5, there's my scalar, times 3, my integer, I get 1.5. 1.5 is not an integer. So here's a scalar times my integer. I don't get another integer. And so therefore z is not closed under scalar multiplication, and therefore it's not a subspace of the real numbers.